So moment of inertia, we're looking at how this mass is distributed over the spinning object, okay? And I've got a little handout here for you that has a bunch of different equations for moment of inertia, because every kind of shape has a different equation. Every distribution of mass has a different one. So these are kind of the most common ones. But I will tell you, they're not ones you have to necessarily memorize, because they're so diverse. Typically in moment of inertia problems, they will give you the equation you need to use for it. It will say it has a moment of inertia of 1/2 mr squared or whatever. But that's just for our reference while we're doing some problems.
Is that good?
Yeah, of course. No, I think that's a great idea. So inertia, basically, we're looking at how is the mass distributed from the axis point. Okay, here is the equation for inertia. The most basic one we have is mr squared. Okay, inertia, moment of inertia is just capital I. Okay, just capital I, and it's mr squared. And so this particular equation is for a hoop-like shape. Okay, a hoop shape. So when we say a hoop shape, it means that the mass is distributed outward from the axes. There's like empty space and then a mass swinging around the outside, just like a hula hoop, right? That's what we're looking at. Could be a light string with something on the end. Yep, like a baton, right? You envision a baton, it's got two things on the end. That would be making a hoop shape. This equation here is under the assumption that we just have one object. So a baton really wouldn't fit into that. It would be like if, it's hard to think about an example here, but if you have a baton, we would have to solve for the moment of inertia of this mass, and then we'd add them together, because you have two objects that are making that hoop shape. Does that kind of make sense? But if you look on your little sheet, all different shapes have different ones, but they have in common this m times r squared. So the units for moment of inertia just end up being kilograms times meters squared. Okay, because we're taking mass times a radius squared. Okay. Here is how we now can connect this idea of torque and moment of inertia. Okay, and so this equation right here, and I'm going to rewrite it because this one's written a little bit funny, but T equals I times alpha. Torque is equal to inertia times alpha. This perfectly mimics Newton's second law, which is force equals mass times acceleration. Right? You see how those two kind of mimic each other? To find torque, you take the force applied times radius of something. Inertia has to deal with mass, and alpha has to deal with acceleration. So they mimic each other really well. Okay? This equation, T equals I alpha, is going to be the basis of a lot of our angular problems. Okay, it just, things fit into that equation really well. It allows us to solve for torque, it allows us to do angular kinematics, and it allows us to look at how things are spinning. So this equation becomes the basis of a lot of what we do, and we kind of sub in and out of there, just like we did with our net force equation, right? We're able to put in for torque, right? If this is this, I could plug in FR sine theta for torque equals mr squared times alpha, right? You see how I subbed that stuff in for torque and for moment of inertia? That equation can end up expanding a little bit, just depending on what we do, okay? All right, moment of inertia is the measure of an object's resistance to angular acceleration due to applied torque. So we're going to look at how this is effective. This guy's got a little video. If we look at the diagram here and we release the blocks from rest, which block do you think will land on the ground first? Any thoughts on this one?
The left.
Okay, why do you think the left?
Because it's more spaced out.
Okay, Macy, thoughts?
I would say the right because of the direction it's going.
Mm-hmm.
If the block were to be released, I think the left would kind of go up a little bit, but the right is already pointed downwards.
Okay. Okay. It's going to be this guy right here, the one on the right. Okay, and that's because the moment of inertia here is smaller. It has less resistance to change than the other because the radius is smaller. Okay, because those weights or those masses are tighter to the axis point, it spins easier, right? There's less resistance to change there. Okay, so when we have a smaller radius, we see that moment of inertia decrease, and so it's easier to spin, right? It's less likely to resist change. So it'll be the one on the right that lands on the ground first. Okay, I don't know, maybe I didn't point that. Yeah, okay, no, I think we're good. All right, let's go ahead and try this. Let's go ahead and try this one. This one is kind of more of a conceptual problem. So this is one that, unfortunately, I do think we could see something like it on the AP test because we don't get a lot of numbers here, right? Remember how on the AP test we have to do a lot with just the variables? We have to manipulate variables. This could be an example of that, okay? So this will help us kind of think through that a little bit. This says small blocks, each with a mass of m, are on the ends of the center of a rod that has a length L. So this whole length is L. And it says the rod has negligible mass. That part's really important here because it's telling us that the mass is distributed on the ends, right? It's not a rod that we're concerned about because that would change your moment of inertia equation. Okay, so if these spin, what shape are we looking at here? Still a hoop, right? Because the masses are on the ends, so it's forming that hoop shape. So we're still going to use hoop. Okay, that's important. So we want to calculate the moment of inertia if the axis is in the center versus if the axis is offset, right? If it's not in the center. So let's go ahead and just look at the first scenario first. Okay, we're going to use the hoop equation for each one. Now, for this guy up here, and for both really, there's actually two masses, right? There's a mass on either end. So we're going to solve for each of them and then combine them. Does that make sense? So these two are identical because they have the same radius from the axis point, but we're going to solve them and then add them together. So let's go ahead and just say, let's label this one 1 and 2, okay? So for mass 1, I would solve for the inertia by taking m times r squared. So what is the radius of this mass, though? If we know this whole rod has a length of L, what's the radius then? 1/2 L, yeah, or L over 2, or however you want to write it. So instead of r squared, we're going to plug in, instead of r squared, we're going to plug in 1/2 L, and that whole term needs to be squared. Okay, do you see what we're doing there? Just using variables, but getting things plugged in. So if I go ahead and do the math there, that would leave me with m times 1/4 L squared. Do we agree with that? Because 1/2 squared, I believe, is 1/4. Okay, so if I was going to rewrite that to keep the coefficient in the front, it would just be 1/4 ml squared. Okay, are we good with that? Okay, what would be true about mass 2? Would it be have a different moment of inertia or the same moment of inertia as mass 1? The same, right? So we can just say we can go ahead and write it the same way. So mass 2 has the same moment of inertia, 1/4 ml squared. So if I was going to look at the moment of inertia of the whole system, I would just add those things together. Okay, and so when I add those things together, I get 1/2 ml squared. Okay, do we see how that works? Why? Do you understand why it's not like 2m or why it's not m squared? Right? Think of this whole system as just an x. So if I take 1/4 x plus 1/4 x, I just get 1/2 x. Right? Do you see what I'm saying there? We're not manipulating that m and the l anymore. So that's that one. On the bottom one, on part B, the difference is that our axis is offset. So if this is still object 1 and this is still object 2, we've got differences here. Okay, so for object 1, it would be m times r squared. So what is the radius of this one in this case? 1/4, right? 1/4 L. And so if we run that all the way out, we get 1/16 ml squared. Okay, and for our second object, we would take m times 3/4 L and square that term to be expanded out. Let's see, 3/4 squared is 9/16 ml squared. And so when I combine those to find the total moment of inertia, that would be 10/16 ml squared, or we could reduce that down to 5/8 ml squared. Okay, so which one of those has a greater moment of inertia? A larger. Which one's larger, 1/2 or 5/8?
5/8.
5/8. All right, so this one would be more difficult to get going and to stop. So it would be easier to get going and to stop. Okay, good. So a little tricky there because we didn't get a lot of numbers, but we can still manipulate that equation even with those variables. That's a very typical AP style question, right? We see that a lot with those variables. That one. All right, let's go ahead and try one here. Let me erase my work. All right. This one says a torque of 12 Newton meters is applied to a solid uniform disc. So why is that important information for us? It tells us which moment of inertia we need to use, right? So solid uniform disc right here. But also look down here, it gave us to us, right? But does it match the one we have on our sheet? Solid uniform disc and solid uniform cylinder, same thing, right? Because a disc is a cylinder shape. So 1/2 mr squared. The radius is 0.5 meters. It accelerates at 5.7 radians per second squared, which would be alpha. So 5.7 radians per second squared. And they gave us torque is 12. What is the mass of the disc? That's our question mark, okay, what we're solving for. Any thoughts on how we could start putting this into play? Any like starting equations?
Would you try to find inertia?
What do we have that connects torque and inertia?
The equation torque equals inertia times acceleration.
Yep, bingo. T equals I alpha, right? We have alpha and we have T, right? So that allows us then to solve for the moment of inertia and then come up here and be able to solve for the mass, right? So it's going to take us 2 steps, but we are given T. My T looks kind of funny, more like a J right now. Okay. T equals I alpha. So we were given our torque as 12 Newton meters. Moment of inertia we don't know and can't solve yet. 5.7 radians per second squared would be our alpha. And so we get a moment of inertia of 2.11. Remember the units here are kilograms times meter squared. And so once we have that value, now we can start looking at this one. Moment of inertia equals 1/2 times m times r squared. Okay, so 0.5 times 0.5 squared gives me 0.125 m. It's 2.11. And so the mass we get comes out about 16.88 kilograms. A equals radius times alpha. And so that gives me an acceleration of 0.36. And what would our units be for that one?
Meters per second.
Good, meters per second squared. Yeah, that's tricky.